Let's look at some history of instabilities in ISRO liquid engines. I'm going back in time in some ways. Some instabilities were observed at the high altitude test facility at Sriharikota range until about 1984 1985, and some, of course, were also uncovered in Vikas engine. There was a combustion system at the high altitude test facility as a route to get ejector operating so that the pressures for the test motors will become low in the test chambers. The third stage rocket motor was tested in this facility, and this facility essentially used a rocket engine based on a German design. The design is some radial injector, somewhat like the Vikas engine, used turpentine and diesel at some rate as the fuel, and red-fuming nitric acid as the oxidizer. And after the combustion was completed, injected water so that we would get steam at high pressure, and this would become the agent for creating the ejector action. So nominal pressure was 21 atmosphere. When it was operated, there were occasional instabilities. What they discovered in the hardware were something like cracks at several places on the injector head, and this damage on the injector head, there were doubts whether it is instability or heat transfer related problem, because what ultimately you see is the damage, and it can be due to a local high heat transfer. So this subject was of debate, took place in Vikram Sarabhai Space Center for a long time, and I happen to be a member of a committee, and there are other members from both VSSA and Institute of Science looking at this problem. After discussions, I just decided to probe the data which was available at SHAR to answer the question whether the failure was correlated with high frequency instability or is thermal problem the cause. There were essentially 15 useful tests at that time. The high frequency instability data was not known for 6 tests. These are periods of inception, and not much of instrumentation was put together. And high frequency transducers were introduced later. It seems to be so. There's a colleague of mine by name Professor P.J. Paul, and somebody from Vikram Sarabhai Space Center liquid propulsion group called Ayyappan Pillai. They spent a month at Sriharikota and did a detailed and careful spectral analysis of the pressure time data at SHAR. The frequencies identified essentially were the first tangential mode at 2.3 kHz, and the second tangential mode at 3.6 kHz, and the first radial mode at 4.6 kHz. But the most dominant one was the first tangential mode. Also, they showed that whenever there was a high frequency instability, there was failure in the 7 tests. When it was clearly known that there was no high frequency instability, there was no failure. One quick check that was told to us that they did was, whenever there was a screeching sound which they could hear outside the test bay area, they knew that they had a problem, and invariably it would lead to high frequency instability. So if there was no instability, the spectra analysis showed somewhere near DC, and the rest of it is white noise. There's not much that was happening all around during the burn time. However, when there was instability, you could find amplitudes at specific frequencies that I mentioned a little earlier, 2.3, 3.6 and 4.6 kilohertz. Okay, you may ask the question, what happened afterwards? We did analysis, we recommended some changes to be done, and they also did additional changes, changed the O by F to some small extent, and by changing the RFS sizes, and it seems to have removed the instability, and the system operated for a reasonable time. But when the major test facility came in Mahendragiri, this particular facility got shut down because it's small. The facility at Mahendragiri was much larger. The Viking engine, it is essentially, the Indian version is called Vikas engine. I must say was never proved to be dynamically stable. The second test launch which took place from French Guiana of the Aryan vehicle had a problem of instability. Like again, a committee was appointed, large number of tests were done, and the final recommendation was adopted in the system. But what was done essentially was that they found that the combustion was very intense, very close to the injector. they said that we will actually make sure that the combustion gets delayed to a slightly downstream zone, and the only way of doing that, which is in their control, was to increase the RHS diameter, which is what they did, and those details are also made available to Indian counterpart, because the Indians worked with the team during the development in the early stages, and so that is how the Viking engine has been functional over a period of time, and the Vikas engine also has the same benefits. Okay, let's look at what the tangential mode and the structure and behavior is. If you look at tangential mode instability, you will find that in actual experiments, you will find a traveling tangential mode means the wave, high pressure wave, will move around like the way shown here. It's also possible that it's a standing mode, which would mean that the mode will go from one end to the other end, as you see in these sketches. The spinning mode is far more fierce and destructive, and with near axisymmetric configuration, this is perhaps the most likely experience that one would get if there was instability. This yeah. What is this image? These are the images on a system where tangential mode instability has been simulated in a model system, and pictures taken of the flame structure inside. You see the intense radiation here. It's like a radial injection? No, these are axial injection. But the particle or the species are getting transmitted and getting traveling all over. The combustion. Yeah, correct. You'll see this paper, you'll get to know the details. Okay. Now, as I mentioned here, the standing mode is somewhat like the longitudinal mode, but on the nodal direction. You see, longitudinal mode in a rocket engine would be in the axial direction to the nozzle, but the tangential mode, which is standing mode, is somewhat like the longitudinal mode, because you will find it moving radially across. And one should not imagine it to be the radial mode, because in the radial mode, it turns out that the pressure fluctuation, as I shown here, is the same. The pressure is the same all around the azimuth or the periphery, and it only radially changes. But in this case, the pressure wave travels from one end to the other end along the radial direction. So this is the difference between the standing tangential mode and the radial mode. Okay. If you look at the data on instabilities of earlier rockets, that is, you have fair amount of information in literature. There is a document called SP194, 8113, and several others from Russia and other places. You can infer qualitatively the following features. The hypergolic propellants in an unlike impingement mode experience the greatest instability. We'll look at possible reasons little later. Propellants injected in unlike impingement mode must experience larger instability, but these are not hypergolic. Non-hypergolic propellants, you can still inject them in a unlike mode, fuel and oxidize. Propellants injected in a like mode, fuel and fuel, oxidizer and oxidizer, they are stable next. Propellants injected through closely spaced coaxial injectors must be very stable. Propellants injected coaxially with one propellant as a gas must be the most stable. This is what you will infer from looking at the information. We will see the meaning of these statements through this downstream or whatever I am going to say. Also, given an injection framework, injector diameter, pressure drop, there is a pressure boundary below which combustion process is stable. Given a pressure, actually one can alter the injection framework, normally coarser injection that provide for stability. This is exactly what has been done in Viking Engine. Finally, the thesis is that creating a uniform, homogeneous heat release profile in the combustion chamber leads to the most stable operation. If this is difficult, minimizing the deviations from uniformity to possible extent helps. Keep this thought in mind, because this principle is not something that you can prove right away. it may need to be, efforts may need to be put in to prove that, but this is the principle which is a guiding principle drawing the conclusions which I have stated here. Well, we'll ask the question, impinging injectors versus coaxial injector. F1 engine, very famous, extremely well written about in the literature, and this is the RD180 injector, written about not as much. Both use LOX, kerosene as propellants. F1 engine injector has more than 2,800 injector holes here, doublet injection. You have these baffles located here, radially and also peripherally in this manner, which separate them and give, it's stated that it gives them stability, and they have come to this conclusion after an enormous number of tests. And in this particular case is doublet injection. They have tried variety of injection systems. These are coaxial elements, not as large as this, 271, and these diameters are large. Okay, and you see oxidizer pre-burner products come in the coaxial zone, and the kerosene is injected in the side. This is the way in which the injection takes place. In the impinging injectors, experiments have been done over a large range of the geometries which have been put together in experiments, and you will discover that if the injector holes are like this, they are located like this in a chamber, as to what it means and at an angle. Now, they have found in these experiments where they have used sometimes gaseous oxygen and gaseous fuel like methane and oxygen and so on, the results are that the 1 and 3, as you see here, they are pretty rough in their, rough means essentially tending towards instability. And in this particular experiment, they have essentially used liquid sprays using kerosene, and they interact and respond to fluctuations in 1 and 3, and they conclude that the spray 2 is not good either, but spray 4 seems to be not so bad. So you ask a question, why is it so? The reason is that when the impinging action takes place, the heat release occurs downstream, 30 to 50 diameters of the injector hole, and in that zone you will see the spray fan, which means in this domain you will find fine oxidizer fuel droplets floating around. Now, when there is an acoustic fluctuation which is present all the time because of disturbances in turbulence and so on, they have an opportunity to interact and with the heat release which takes place because of the droplets, and the main heat release distribution is affected by oscillations. There is a heat release profile here, and because of the vaporization and combustion locally, and this interaction which is taking place between this heat release distribution and the acoustic oscillations disrupts even the mean energy distribution, and that is the reason why, and it happens in phase, and that's why you have the instability. So that is why they claim that when the degree of interaction is much more, instability is higher than where the degree of interaction is lower. Okay. Well, if you look at literature and see what is stated in the unlike injection system of the F1 engine, well, you find that this system was developed in late 50s to early 60s. It had something like 207 tests with 11 injectors, 422 tests with 46 injectors, 703 tests with 51 injectors. It's a humongous effort. Observations by these authors, and the cause of instability in F1 engine is a very nice document, and those who want to learn about instability should read this. The mixture ratio gradients produced by this condition of the injection system promote mixture ratio oscillations in the vicinity of vaporizing droplets, inducing burning rate oscillations, which could couple with the acoustic field. Exactly the kind of point which I made a few moments ago. You are vaporizing droplets, and the acoustic oscillations interact with burning rate oscillations, and the coupling produces the instability. In fact, their final configuration increased the RSS sizes for oxidizer in doublets to 6.15 mm, a half in impingement angle, not very large, 20 degrees, and for fuel elements at 15 degrees, and so on. I think viewed from the principle that the thesis that I spoke about, the small impingement angles imply a much lesser lateral velocity contribution and lesser lateral disturbance. Also further, they make a statement, sensitivity towards instability was always observed if major combustion zone was relatively closer to the injector phase, where oxidizer vapor existed in sufficient degree of angular non-uniformity. If the combustion zone was moved to a region downstream where oxidizer vapor concentration was essentially uniform, displacement effects decayed to a level incapable of supporting instability. Almost a different way of saying whatever I said initially. I picked out what I said by reading this. I must also tell you that it is not something born out of nothing. It's looking at all the documents and considering that a simple way of describing what is the most appropriate way of designing the system was what came out of this. If you look at LOX Cryo, LOX-LH to Cryo engine, they have always used coaxial injection, whether it is USSR, USSR. Why? Because the liquid hydrogen is injected as a gas. It goes through a regenerative cooling system, it comes out as a gas. In all likelihood, these special development of Russians, even though they did learn a whole lot from German V2 technology, which appears to be more complex than Russian injector technology, I feel that this is a special development of the Russians. I can't say much more than that at this stage. I mean, you trace back the history, you can't get precise origin of why they chose this design. Because they seem to have chosen it for many other applications, including storable, oxidizer and fuel combinations. Okay, you have essentially, you notice the fact that there is a peripheral hydrogen injection holes. These are for film cooling the surface so that the heat flux that goes into the walls is reduced, and so you get a better protection for the combustion chamber. Further, even smaller liquid engines based on storable propellant combination like RFNA, aniline, xylidine combination used in early Prithvi engine or later RFNA UDMH combination used coaxial injection but with swirl. There is a project which was there in DRDL Hyderabad to re-engineer the vehicle called SA2, and the second stage of that was the liquid engine, which again essentially became the engine for Prithvi in the early parts of the development, and that utilized essentially a combination of aniline xylidine as the fuel and reducing nitric acid as the oxidizer. It essentially used the same kind of design which I showed earlier for LOX-LH2. That swirl. Admittedly, I think even with swirl leading to lateral velocities, the hope is that the cancellation of lateral mean velocities occurs because there are ever so many small injectors on the injection phase. And curiously, no instabilities were encountered in this engine, and this is partly due to the engine being small, pre-turn thrust. I say only partly because this engine had an inner diameter of 200 mm, and with this diameter, other engines with impinging injectors have experienced instability. It may look like I'm making impinging injectors as the bad boys, but that's in fact true.
Yes, sir.
Yeah?
So in the previous slide, you have said that the interaction between the two jets, if it is an impinging injector, it should be several diameters downstream the injector face itself. Thus, you mean to say that there is some pressure oscillation coupling with hydrodynamics that lead to the final heat release.
What is meant is the following. Suppose injector hole diameters are small, impingement occurs closer to the injector face and interaction will be much more intense. The heat release starts closer to the injector face. Okay. Now, when heat release occurs and Do remember, when the sprays interact, there will be always a spray distribution around, with a mass flux distribution which can be variously oriented. Now, if the acoustic oscillations now interact with the heat release profile, and that occurs very close to the point where the droplets are present, mean flow which is obtained for the heat release is in that zone, then the mean free flow field is also affected by the acoustic oscillation. If, however, you take a larger injector hole, then the heat release is pushed to a downstream domain where the lateral flow present in the cross section is not as much as what would happen very close to the injector, and therefore any coupling that takes place will not be picked up by the mean flow, which is virtually axial. So it will not have any tangential component. If there is a tangential velocity for the fluid, and if that gets acoustic coupling, then you have a better chance of creating a tangential mode of instability. But if you make sure that the mean flow in the azimuthal direction, lateral direction is very small, the chances of coupling between acoustic oscillations in the lateral flow field will be very small. That's the logic. Okay, there are other US engines. One is called RS-14 of 81 millimeter diameter. Unlike doublet, it had a high frequency instability 9.5 kilohertz, consistent with the diameter. Lower module engine, 198 mm diameter, not very different from this. It's a triplet, 3.5 kilohertz. Titan S2 engine, unlike doublet, larger diameter, 1.8 kilohertz. So, impinging jet injectors have always had the problem. Also, these engines use hypergolic fluids, and heat release is almost instantaneous and leads to significant mean lateral velocities, and therefore the coupling takes place. This is the logic. Kulik, who is a distinguished academic from Caltech, in fact, he has written an article and he describes many aspects of high frequency instability in liquid rockets. And on the Russian RD 0110 engine, he states, coaxial swirl injection elements were used with emphasis on injector dynamics. The combustion instability was rare in the final design, but did occur randomly during the ignition transient, observed during the qualification tests. Now, this is in fact an argument made saying that they also used to provide baffles, but they provided the baffles in an interesting way. They just introduced the oxidizer posts or the injection holes into the combustion chamber in specific directions so that you have essentially baffles created. But I think the extent of preoccupation of most studies in America, including those influenced by Professor Kulik, seem to have bypassed, I think, the eminent features of coaxial injection. And it doesn't seem that he was very happy, very wonderful. It is okay, they have done something. That's the situation. Though there are telltale observations in writings leading to importance of coaxial injection, they have not been set into a principle to follow by which the design is created. See, if you do not make this statement emphatically, and literature is full of many statements, you will get confused and you will have to ask the question, whom do I trust? So these are the problems which arise when you go to complex designs. I also want to say that American research goes much greater sway, and we don't have access to Russian technology and academic discussion probably because of the language. And I think we have not been able to derive enough benefit for recognizing the coaxial injection approach. But Elon Musk, is quite smart. He figured out that the Russian technology is good. He benefited from them. And in fact, he is building an engine of LOX methane at much higher pressures of 300 atmospheres using the same class of ideas called the Raptor engine. There is a very interesting, what I consider as neglected, stable German experiment. You'll see the reference here. What they did is he had two combustors, you can see, a small combustor, 80 mm by 80 mm. One of them had baffles, one of them did not have baffles. And you see the details. In one case, no, and in one case, yes. And if you see that in this particular design, they had high combustion efficiency, all of it was stable. the oxygen to fuel ratio is 5 to 6, typical of LOX-LH2 engines. I'll say a little more. And the pressures are high, going up right up to 90 atmospheres. Okay. And if you see further, they did also perform experiments where the hydrogen as a gas was let through the small ports, and this is called riggy mesh, and LOX post also was introduced so that what they claim as cheap pipe material, this is just copied from their paper. The holes for the LOX post were simply drilled into porous plate, etc., etc., and they found that the system was quite stable. And the argument that they have given is, if you look at the propellant mixture ratio, in one case where there was instability, the variation was much more than in the case where there was no instability. You will read it here. Changes in the LOX pattern from this, black or grey, and estimated radial mixture ratio distribution across the injector head. And you can see that the one which was stable belonged to this particular design. You can see that AP 180 168 V2 grade is the one which produced V2, the one which is very stable. The reason, therefore, is that you make the mixture ratio uniform. Making mixture ratio uniform also means that the lateral distribution is not, velocity distribution is not very much, the whole flow is axial. So, in this study, large number of injection for oxygen, the porous wall through which hydrogen is injected at temperatures as low as 45 K. Perhaps it's also good to know that there is a well-known stated principle that instability will be much more when the liquid hydrogen temperature, when the hydrogen injected at a lower temperature, compared to higher temperature. So people do experiments. What is the temperature below which you get instability? So they keep reducing the temperature and find out at what temperature you get instability. And that temperature, for example, injection in the engine which we built at LPSC, the injection temperature is more than 100 Kelvin. And you see, even at temperature of 45 K, they found it to be stable. It has a certain contraction ratio and so on. And therefore, it looks like what drives the instability is simply the fact that the lateral mean flow on which acoustic flow field really works on, and therefore this leads to coupling, which is unfavorable. Okay. I think the most crucial aspect of the O-wave distribution is made uniform across the cross section. I think I've said what I need to say about liquid rocket engine. The ideas are very similar, and you will discover this in the case of gas turbine as well, afterburners as well. Let me look at this. This is a gas turbine engine taken from GTRE's documentation. You have the flow coming from the turbine, and you will find a number of holes, a perforated sheet here. As I mentioned earlier, it becomes acoustic absorbers. Then you have a geometry where fuel is injected, you have spray bars to inject the fuel, and you have flame holders here, large number of them around the periphery. And this is the cone, and the flow comes like this, gets mixed, then fuel is injected, combustion takes place here and goes out to the nozzle. Now, this is a serious problem, first tangential mode. I think I mentioned this earlier. In an earlier presentation, I brought out all these features. This instability occurs despite acoustic damping provided by the perforated liners. The Helmholtz effect of the gases coming in from the outer periphery through the holes, taking away the acoustic energy, is also applied here, and they have used advanced design tools to get to that, and yet you find the instability being present. And there is an interesting Italian work which you will see referenced here, 1998, and it is titled Afterburner Design and Development, and you will find this passage which I think is worthy of being read and understood. the turbine exhaust diffuser, that is the gases which deliver it to the afterburner. This component placed downstream of the low pressure turbine exit has different purposes. One, to recover the residual flow swirl at the turbine exit in order to ideally feed the afterburner core with no swirl flow. To reduce the flow velocity at the entry in order to make combustion in the core stream stable. To straighten the flow in order to obtain a flow ideally parallel to the engine center line, maximizing the engine thrust. The first of these functions is obtained with a row of vanes located upstream of the conical diffuser and giving a counter swirl angle to the flow. The word counter swirl is used because any flow which comes out of the turbine will have a certain swirl. Because the rotation of the turbine blades, you will find a swirl. So, you need to put in some effort of design to make sure it is axial. That is the statement made here. If you look at the actual situation in the afterburner, this is data which was provided by GTRE for the first design which they had put together. You see the swirl angle which is presented here is plus 10 in the outer part and is minus 10 in the core. That means, the flow comes in one direction, in the opposite direction it swirls in the core. In fact, it is quite contrary to what you expect to get stable combustion. So, if you are desiring it for instability, you should do what is being observed. So, this was done without necessarily appreciating this particular effect, and what more, you will see that the pressure profile for the current situation is like this, whereas the expected pressure profile from a benchmark design from Rolls-Royce is like this. That the pressure must be uniform, flow rate must be uniform, is what the expectation is. Okay? But if you violate that, to some extent it will work, but if you violate it much more, it will kick back and give you instability. That is the inference. Okay? Therefore, if I have to sum it up, for liquid rockets with storable semi-cryo or cryo propellants, it is correct to choose coaxial injection strategy with reduced swirl to minimize lateral mean flow and create a uniform mixture ratio as much as possible. Reduced lateral flow reduces coupling to acoustics and so incidence of instability. For gas turbine afterburners, one should create a near uniform flow from turbine exit to the afterburner. Also, I must tell you, the GTRE team took their afterburner, it was tested in Russia. There, the connected pipe mode test had uniform flow. There was no instability. There is a proof of this idea came out in the actual test. But if it was known that alone was responsible, then you will take the corrective action in that direction. But if you were not sure that that is the only thing that is responsible for your instability, you will keep looking at many other reasons and therefore geometric features which may be responsible. Okay. So, also fuel injection system should help create uniform heat release across the section of the afterburner as much as possible. What is the message as far as I can see? There is so much of literature on instability and it can cause loss of direction if not carefully contemplated upon. It is perhaps good to trust Russian design, but I think we must also have an independent adequate justification. What do you mean by justification? If for example, a manned flight is contemplated, it is necessary, I think one should have an extension of the steady state model to instability, perhaps using larger dissimulation to answer many questions that may arise when a propulsion system is integrated into the manned launch vehicle. This was not available earlier, so people had to go by trust, saying I know it works, so slowly and steadily the confidence improves in the person and whatever he says is accepted. But we must move away from that, we must have a design tool, and the design tool must be capable of being used by many, and therefore you get confidence come from that analysis. I have described some references here for the work, and this concludes discussion on tangential mode instabilities in liquid rockets.